In this video lecture, I'll introduce the correlation of rock layers. Matching of rocks of similar ages in different regions is known as correlation, and to develop an understanding of the geologic history of the entire Earth, rocks of similar age in different regions must be matched up. Typically, geologists correlate formations between nearby regions by rock types. We call this type of correlation lithologic correlation. And before deformation or erosion, the layers that correlate may be continuous. And here we can see that layer Z from location A matches or correlates with layer Z from location B. And these rocks correlate with those at location C. In some cases, a sequence of rocks contains a key bed or a marker bed, and that's a particularly unique layer that really provides a definitive basis for correlation. So maybe this type of sandstone Y has a certain mineral composition and texture that matches or correlates exactly with sandstone Y in location B and sandstone Y in location C. To correlate rock units over very, very broad areas, geologists often rely on fossils to help define relative ages of sediments and correlate them. Fossils can be very useful because the source of sediments and depositional environments may change from one location to another. So here we can see at the time of deposition, right, locations A, B, and C were in different parts of a sedimentary basin. And in this instance, limestone in location A that correlates with limestone at location B has pinched out over here in location C. As a result, we can see there is no limestone in this location here of stratigraphic column C. And again, that's because the limestone had pinched out. Not only can correlation provide an understanding of the geology over a very, very broad region geographically, but it can also help provide a longer history or a more complete history by comparing partly overlapping sections. So in this example here, we can see how we have the correlation of rock unit 4, the correlation of rock unit 5, and the correlation of rock unit 6 in these two separate stratigraphic columns. By correlating these and utilizing both sections, we can see how we obtain an understanding of older rocks and younger rocks when we use these sequences together. A great example of comparing partly overlapping sections is the correlation of strata among the national parks of Arizona and Utah. And here we have rocks from the Bryce Canyon, Zion Canyon, and the Grand Canyon. And we are able to correlate rocks from Bryce Canyon to Zion Canyon and Zion Canyon to Grand Canyon in this fashion. And you can see how not only is there a much larger representation geographically, but also a much longer complete history when we match or correlate these overlapping units. And here we can see a nice example of a cross-section showing Grand Canyon, Zion Canyon, and Bryce Canyon. And again, the overlapping of these units to provide a very long and comprehensive history of this area. Here I have a geologic cross-section of the northern part of the state of Florida. You can see this cross-section extends from A to A prime. And if you look at the map of the state of Florida in the upper right-hand part of this slide, A to A prime extends from the west to the east part of northern Florida. And this geologic cross-section was developed by obtaining 12 soil moorings. You can see they are actually numbered on the bottom here, 1, 2, 3, 4, 5, and so on to 12. And in each of these soil borings, geologists obtained the subsurface geology in these 12 locations. And then from these soil borings, they were able to correlate the subsurface in location 1, matched it, correlated it to the subsurface in location 2, and so on to establish a geologic cross-section of this transect, the transect of northern Florida. This was also done for a transect that extended from the northern to the southern part of Florida, from B to B prime. And this transect, this geologic cross-section, was developed utilizing information from 11 soil borings, right? Again, numbered on the bottom of the cross-section here. And geologists obtained information from the subsurface in boring 1 and correlated it to the subsurface in boring 2, 3, and 4, and so on. And in this instance, we can actually see a very large anticline, right, by correlating information from all of these soil borings. Your final project involves creating your own geologic cross-section, very similar to this, by graphing and correlating soil boring data I will provide. So I'll be providing you data from 5 different well logs. And essentially a geologist went out, drilled 5 wells in a certain area to identify what was in the subsurface at these 5 areas. And they recorded their information in these well logs. In this location, the ground surface is actually at 2,400 feet above sea level. That's the ground surface. And you can see how the geologist dug into the ground, right, working lower and lower and lower, 5 feet above sea level to the bottom of the well. So in well number 1, the soil boring extended from 2,400 feet above sea level down to 400 feet above sea level. That's the bottom of the well. And you can see they were different units of rocks within the well at this location. Unit 1, Unit 2, Unit 5, Unit 6, and Unit 7. So here we have 5 different types of rocks, and some of the contacts between these rocks were horizontal, and other contacts dipped. You will start your line, right, by correlating information from all of these soil borings. Your final project involves creating your own geologic cross-section, very similar to this, by graphing and correlating soil boring data I will provide. So I'll be providing you data from 5 different well logs. And essentially a geologist went out, drilled 5 wells in a certain area to identify what was in the subsurface at these 5 areas. And they recorded their information in these well logs. In this location, the ground surface is actually at 2,400 feet above sea level. That's the ground surface. And you can see here the geologist dug into the ground, right, working lower and lower and lower feet above sea level to the bottom of the well. So in well number 1, the soil boring extended from 2,400 feet above sea level down to 400 feet above sea level. That is the bottom of the well. And you can see they were different units of rocks within the well at this location. Unit 1, Unit 2, Unit 5, Unit 6, and Unit 7. So here we have 5 different types of rocks, and some of the contacts between these rocks were horizontal, and other contacts dipped. You will start your final project by first plotting the data from your well logs provided onto the graph that I have provided, which looks something like this. And you'll notice on the graph, I have indicated the location of your 5 wells, well 1, 2, 3, 4, and 5 respectively. Note that the ground surface is right up here at the very top of your graph. This is your ground surface, and you will be plotting the contacts of the different rock types in the subsurface at each of these locations. You will want to definitely pay attention to the dip angles for rock units that are not horizontal. And I have helped you out by drawing the contact in 2 locations here. This will make much more sense as you get started. But these dip angles that I have drawn for you here are dip angles that are of 23 degrees. So that'll come in handy if you don't have a protractor. No worries, you can just utilize the same angle as I have provided here for you. So here in well number 1, specifically, you will be plotting this data. So if we got started here together for a moment, from 2,400 feet above sea level down to 2,100 feet above sea level, we have Unit 1. And I recommend that you start by drawing some tick marks on your cross section in this fashion, and then specify that that is Unit 1. And Unit 2 extends from 2,100 feet above sea level to 2,000 feet above sea level. So I had given you the tip in your handout this week to angle the contacts between rock units to match the dip that I have specified. And when you have plotted all 5 wells, so you've plotted data from all 5 wells, at that point you can correlate or match rock units from one well to rock units in another well. And the objective is to generate a geologic cross-section of this area. You will then utilize the geologic cross-section that you have designed to answer a series of questions for your final project, one of which is to relatively date the sequence of events in this cross-section and tell the story of the geologic history.